Everyone, we're looking at class number 48 here. Let's see. Our goal is to explain how the force of gravity attracts satellites to the Earth without them crashing into the Earth. So to start class, what we did was we calculated the force of gravity between the International Space Station and the Earth. So we drew a little picture here on the left. Now, one really important concept here is what is the value for R? How far is the satellite from Earth? Now, R is not 408,000 meters. R is the distance from the satellite to the center of Earth. So it's not just, so this distance right here, if I were to mark this off, this distance right here is 408,000 meters. But don't forget, we also have to go to the center of the Earth. So that's the radius of Earth. So to find R, we had to add 408,000 meters to the radius of Earth, 6.37 times 10 to the 6 meters. So we get an R value of 6.78 times 10 to the 6 meters. Our two objects, M1 and M2, there's the mass of the satellite, or excuse me, the International Space Station. M2 is the mass of the Earth. It doesn't matter which one you make, M1 and M2. And big G is our gravitational constant, 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. Now that I have all of my units in my givens, I do not need to include them when I plug them into my equation. So here's my equation. Make sure you write that down. And let's see, we plugged everything in here, and we got about 3.6 million newtons. So the question is, well, why doesn't it fall down if we're pulling down? If the Earth is pulling on the International Space Station with so much force, why doesn't it fall down? So that's something for you to kind of think about and answer there. So we use this simulation here. And what we found was, well, first off, the velocity is always changing magnitude and direction. You might also want to say that the velocity is always pointing tangent to the orbit. Excuse me. So now I wanted you to pause the simulation and take the velocity of the Earth away. Just make the velocity as small as you can on the simulation. If you grab the V on the end of the velocity arrow, you can make the velocity smaller. How does this change the Earth's orbit? Hopefully you notice that the Earth crashes into the sun. So explain how the Earth's velocity prevents it from falling into the sun. So the Earth is falling toward the sun, but its tangential velocity causes it to keep missing the sun. So as the Earth is falling towards the sun, since it's traveling tangent to its orbit, it's also kind of missing the sun, if you will. A really good example here is of this cannon and this cannonball on the Earth. If we fire the cannonball pretty fast, it goes pretty far, but eventually hits the Earth's surface. Fire it faster, well, it's going to fall and eventually hit the Earth's surface. If you fire it fast enough, the trajectory of the cannonball matches the curvature of the Earth, and that's what orbit is. So how does satellite stay in orbit? Same concept. If the moon were to suddenly stop moving, describe what happened to it, it would crash into Earth. So the only thing keeping the moon up in the sky is the fact that it's moving. If the moon were to magically stop moving, or if we put like a big brick wall up and the moon hit it and the moon stopped, the moon would come crashing down. In the last part here, if there is a black hole at the center of our galaxy, why don't we get sucked in? Black holes are really strong. Why doesn't everything just get pulled in? And the answer is actually similar to what we've been discussing today. We're moving, okay? And we're moving really fast. So not only is the Earth moving around the sun in orbit, the sun is moving around the black hole at the center of our galaxy really fast. I think something like 220 kilometers per second. I think it's like 490,000 miles per hour. If the sun, though, were to just stop, right? If it just stopped moving and our whole solar system stopped moving together, we would go right into the center of our galaxy. It would fall right in.